The aim of this video is to present the simplest version of the real business cycle model with which one can analyze economic fluctuations that go back to real technology shocks, basically, or shocks on the real side of the economy, not nominal shocks related to monetary variables, basically. Textbook treatments of the real business cycle model can be found in the book by David Romer, 2018, Advanced Macroeconomics, or in Ben Hydra's book, 2017, Foundations of Modern Macroeconomics. And the original article on which this chapter is based is by Finn Kydland and Edward Prescott from 1982, Time to Build and Aggregate Fluctuations, published in Econometrica, which is basically one of the first such real business cycle models, and later the two got the Nobel Prize in Economics in 2004 for their contributions to the theory of real business cycles. The starting point of this literature is basically the ISLM model and the Phillips curve that you all know from introductory macroeconomics, that together are also often called the ASAD model. And these very simple models, actually, that are not micro-founded but rather ad hoc, nevertheless manage to explain some aspects actually of economic fluctuations surprisingly well. However, they fail in some respects, and particularly in the 1970s, the Phillips curve relationship broke down, and one found out that it cannot be exploited by economic policy, so there is no trade-off in the sense between inflation and output growth. And that was also one of the reasons why the large-scale macroeconometric models that were based on these relationships failed rather spectacularly in the stagflation period of the 1970s and beginning 1980s in predicting how the economies would evolve. All this has led basically to the Lucas critique, the famous Lucas critique, that actually the behavior of people changes when underlying variables change. So if we want to perform economic policy by exploiting some of these relationships, such as the Phillips curve, then basically these descriptions would break down because individuals would actually change their behavior. So, for example, if monetary policy is expansionary, then people might expect higher inflation. And this change in expectations itself has a strong potential to counteract the effects of the policy itself. And that might be a reason for why the Phillips curve broke down in the 1970s. And this has led to demands for frameworks that take the decisions of individuals better into account, so that are micro-founded and from which optimal behavior of individuals is somehow derived, that just depends on so-called deep parameters. And then if there are some changes in the economy, say due to exogenous policies, then households and individuals would react in some optimal way to these changes. And therefore, these behavioral equations derived from such household optimization frameworks would lead to a micro foundation and would lead to a situation where households could react to changing economic policies. And providing such a framework was addressed in the research agenda of Finn Kydland and Edward Prescott, for which they, as I said, already received the Nobel Memorial Prize in Economics in 2004. And in a nutshell, they came up with a real business cycle model that is at its core a Ramsey-Cass-Koopmans model that takes, however, fluctuations into account, and these fluctuations are driven by real shocks and people's optimal responses to these real shocks, in particular responses with respect to labor supply. Now, how do these real business cycle models look like? What we will do now in this chapter is to generalize the Ramsey-Cass-Koopmans model that you already know from the previous videos by incorporating three additional issues. First of all, expectations to allow for uncertainty, because there will be fluctuations later on that are driven by exogenous shocks. So therefore, rational households will form some expectations about the evolution of variables in the model. Then the second generalization is that we will endogenize the labor supply decisions of households to investigate the effect of fluctuations that are driven by exogenous shocks on the decision of households to supply labor, actually. So on basically, if you will, involuntary unemployment. And then, yeah, by allowing for these exogenous shocks in the first place, and the most important one is a shock to total factor productivity, so that are the so-called technology shocks. What are the basic assumptions? Now, in contrast to the Ramsey-Cass-Koopmans model that we know from the previous videos, time is assumed to evolve discretely. So that's often the case in business cycle models, that they are written down in discrete time. There are also continuous time business cycle models, but they are much rarer actually than discrete time business cycle frameworks. Markets are perfectly competitive. That's as we had it before. The shocks that we will analyze here in the basic model, they only affect total factor productivity. So these are technology shocks. Later on, we will see that one can allow for many other different shocks, for example, to policies or to preferences and so on and so forth. And of course, these generalizations then often also lead to predictions that are more in line with the data than a model that only allows for technology shocks. And new Keynesian models that we will discuss in another video later on, they do not only include real shocks to policies or preferences or productivity, but also nominal shocks to include, for example, frictions so that prices cannot change instantaneously, and then money supply shocks will also have effects on real economic output in the end. But we will see this later on. We start the model description from a mathematical point of view by having a look at the firm side. And the firm side is again, as in the Ramsey-Cass-Koopmans model with technological progress and the Solow model with technological progress, described by such a Cobb-Douglas production function as we have it here, where aggregate output at time t, yt, where the subscript here denotes time, and we use the subscript notation for a discrete time notation, is produced with physical capital at time t with an output elasticity of alpha, with labor with an output elasticity 1 minus alpha, and again, technological progress is labor augmenting. So A multiplies with labor in the production function, and an increase in the stock of technologies increases the productivity of labor. Since markets are perfectly competitive, the factor rewards are the marginal value product of the corresponding production factor. So if we want to have the wage rate, we take the derivative of the production function with respect to labor. Now this is just 1 minus alpha comes down from the exponent. Then we have k to the power of alpha, which remains unchanged. At times Lt, the exponent is reduced by minus 1, so we have At times Lt to the power of minus alpha that remains here. So we can put Kt and At-Lt into the same term within parentheses here and raise it to the power of alpha. And then we have the inner derivative of this expression here with respect to L, which is technology. So that's the stock of technology. So that's the wage rate. And with respect to the interest rate, we have that it's the marginal product of capital minus the rate of depreciation. The rate of depreciation is denoted by delta, as we also had it previously. And the marginal product of capital is the derivative of the production function with respect to k. So that's alpha comes down from the exponent. K to the power of alpha is reduced by 1, so we have alpha minus 1 in the exponent, and At-Lt remains here, so we can rewrite it in the denominator and raise it and multiply the exponent by minus 1, so we get this expression actually here, and then we have the interest rate. Next, we specify the evolution of some important variables in the model. And here it's probably important to note that David Romer used the notation for growth rates in terms of growth factors from continuous time. So that would be an approximation actually to the discrete time growth factor. So if a variable grows at rate g, you can write it e to the power of g times t in continuous time, and in discrete time you would write 1 plus g to the power of t. So actually we would have this notation here, But if the growth rates are small and the time steps are small, which we have already seen also, then such an approximation can be done. And Roma in his book writes it down in this way. So he has the growth factors as they are written down here in continuous time, but I changed this to a discrete time formulation actually in most parts of the model later on, just that it fits better to the model itself that is written down in discrete time. The population size then evolves according to the growth rate of the population, denoted by NT. So NT at the time T would be N0, so initial population size multiplied by 1 plus the population growth rate raised to the power of T. And then if we take the logarithm of that and we use the approximation actually here, then we would get that the logarithm of the population at time t would be the logarithm of the population in the initial period plus the population growth rate times t. So that's also based on this approximation here. And technology evolves also according to a growth rate that is denoted by GT. So we have that the stock of technologies at time t is the logarithm of the initial stock of technologies at time 0 plus the growth rate times the amount of time that has passed since time 0. And then here the technology shock is introduced. So AT tilde is an exogenous shock to the stock of technologies that hits at time t. And this is basically stochastic following an AR1 process, an autoregressive process of order 1 with an autoregressive coefficient of rho a. So if the shock hits and we have a positive autocorrelation, then it takes some time for this shock to peter out basically. The shock, so the variable here, epsilon at, is the innovation at the time period t. And the correlation can also be negative. So if you have a negative correlation here, autocorrelation coefficient, then basically we would have fluctuations that would lead to fluctuations, as we will see later on. So writing it down in this way, that is basically related to the shortcut formulation that Roma uses, is convenient because it allows us to write everything down in logarithms, and later on we will see that this model is usually solved by taking the logarithm of the variables at the long run balanced growth path, and so having it in this way is quite a convenient formulation. Now, what about the household side of the economy? Here, the assumption is that individuals form rational expectations on the future wages and the future interest rate that we have here, and they discount the future at the time preference rate rho. So that's impatience, and that leads to a discount factor that is 1 over 1 plus rho, which is smaller than 1. So we discount the future, we put less weight on future periods as compared to today, because there is a time preference. So people are impatient, they weigh a certain amount of goods differently. So the farther away in time it is, so they weigh it down, and that's captured by this discount factor. Then we can write down intertemporal utility in expectation. So we would have UT, so that's the utility function, the lifetime utility function of the household or the individual. I use them interchangeably here because as compared to Roma's formulation, I made a simplifying assumption actually that I normalized the number of households to 1. So the population size NT is basically the number of individuals in the economy, and I don't deal with households as such. So the intertemporal utility function is the expectation of the sum over all utilities in the life cycle of the individual from time 0, that's basically the date of birth of this individual, up to time infinity. And then the future is discounted with the rate beta. The further in the future it goes, the higher the exponent becomes. And since beta is smaller than 1, this term would become smaller and smaller and smaller the further out in time the instantaneous utility refers to. And utility itself is derived by consumption. So consumption increases utility, as we always have in the models. But this part is new here. Utility also increases in leisure. And leisure is 1 minus labor supply of the individual, which is denoted by this lowercase lt. And so if individuals work, so we see that's with a negative sign here, that entails certain disutility. And the preference for leisure is captured by B here. So B actually captures the preference for leisure or reflects the disutility of labor, the weight on the disutility of labor, because that's what appears here. So utility is increased by consumption and by leisure, and then we multiply by the number of individuals in the economy. So that would be again a utilitarian concept here, Benthamite utility function basically. Well, and that's the main difference to what we discussed in the Ramsey-Cass-Koopmans model. First of all, that we have to form expectations, and second, that we have leisure in the utility function. What about budget constraint? Capital is the only savings vehicle in the economy, so there are no shares, bonds, or stocks, whatever. It's only capital, and therefore all the savings that individuals accumulate, they are used to invest in physical capital, and they increase the physical capital stock. So therefore, the per capita budget constraint, the dynamic budget constraint, can be written down as it is written down here. We have the capital stock at time t+1 on the left-hand side, and we write it down in per capita terms, so we divide everything by the number of people by the population size. Now this increases with wage income, which is the wage rate multiplied by labor supply of an individual. So that's the wage component of income. We also have the investment income, so the interest income actually, that's the interest rate multiplied by the capital stock that the individual already owns at time t, again divided by the population size because it's written down in per capita terms. So that's then total income of an individual. Now if we subtract consumption, we would get basically what the person saves in terms of her income that she earns on the labor market and by means of investment. But then there are also governmental transfers or taxes, so they could be negative if the government taxes individuals, but it could also be a lump sum transfer, then it would be positive, and it would increase then ceteris paribus individual savings. And then we have here the capital that is carried over from the previous period, which of course also adds to the capital stock of the individual at time t+1. So again, LT is per capita labor supply, CT is per capita consumption, and GT refers to per capita lump sum taxes or lump sum transfers. Now we can write down the Lagrangian for this optimization problem. So that's then the utility function as we have it here, plus the Lagrange multiplier times the budget constraint, where we bring the term with kt+1 to the right hand side basically. And what we see here is that if we divide here by nt, then we could write this as lowercase kt+1, which would be uppercase kt+1 divided by nt+1. But since we only have nt in the denominator, we can actually write this also as lowercase kt+1 multiplied by 1 plus the population growth rate. So that's an equivalent representation, but then we still have everything in per capita terms, so in lowercase letters. The first order conditions now pin down to the following three. First, we have the derivative of the Lagrangian with respect to consumption. Now that's the derivative of the logarithm of c. So that's 1 over ct. It's multiplied by n from here and by beta to the power of t from here. We still have the expectations operator in front of this expression. And we have here minus ct. So we have the derivative of this expression here with respect to ct. All the terms drop out except for this term multiplied by lambda t. So if we take the derivative of that, lambda t remains with a negative sign, and that has to be equal to 0 for an optimum basically. Now we can reformulate this by first of all noting that the expectations operator has the information set at time t. Now we only have variables at time t in this first order condition, so therefore the expectations operator can be dropped out. We don't have any expectations on that have to be formed on variables that would appear with a higher time period here. So the expectations operator is not needed because all the variables that we have here are already known at time t. So then we can just reformulate and would see from this expression here that uppercase nt divided by ct would be equal to the Lagrange multiplier according to this first order condition. The second first order condition is the derivative of the Lagrangian with respect to LT, labor supply. Now this is a little bit more involved because we have this term here in parentheses. We have b here, b times n is again in the numerator, 1 over 1 minus lt would be, so 1 minus lt would be in the denominator, and then we would have the inner derivative, and since lt appears with a negative sign here, we have the negative sign also in front of this expression here. Now LT also appears in the budget constraint here, multiplied by lambda t times WT with a positive sign. So we have this expression here as well. And again, we note that all the variables that appear in this expression refer to time period t. So we can again drop the expectations operator, and we would see that this expression in here would be equal to the Lagrange multiplier divided by the wages. So this here comes to the right hand side, so the negative sign becomes positive then, and the WT appears then in the denominator, and we have that the Lagrange multiplier also is equal to this expression. So it's equal to this expression and this expression, so we can set the two equal to each other on the next slide when we solve for the optimal consumption path and optimal labor supply. And finally, we have the third first order condition, which is the derivative of the Lagrange multiplier with respect to capital at time t plus 1. And now here we have to note that capital at time t plus 1 actually shows up in two places in this whole infinite sum. Namely, here it shows up immediately, so that's immediately clear. So if we take the derivative, we get the first part of this expression immediately. So that's minus 1 because of the negative sign times 1 plus n times the Lagrange multiplier times the discount factor from here. So that's this term, the derivative with respect to this kt plus 1 here. However, there would also be a kt plus 1 here, but in the next period. So that's iterated one period into the future. And what we get here is lambda t. Then here we also have a kt. We can summarize the two together to one term. So we would have 1 plus the interest rate, rt plus 1. So we can summarize them together into this term. We multiply it by the Lagrange multiplier at time t plus 1. And we also have the discount factor at time t plus 1. And that has to be equal to 0. And that's the third first order condition that we need. Now putting together the first and the second first order condition, as I said before. So here we equate these two expressions, n t over ct and p nt divided by 1 minus lt wt, because they both are equal to lambda t. Then we arrive at this expression here, which can be further simplified because nt drops out, and we can bring ct to the left hand side to the numerator and b to the right hand side to the denominator, and we get an expression that relates actually optimal consumption, optimal labor supply, wages, and the disutility of labor, but in a static manner, as we will see later on. So the labor supply decision here is static. It does not extend over different time periods, which is a huge simplification, and actually due to the fact that the utility function involved logarithmic utility without substitution and income effects actually cancel each other off. And together with the consumption savings choice that we will analyze next, this relation will then pin down endogenous labor supply LT, and we can solve for it analytically, even in the simplified framework. Next, we can put the first and the third first order conditions together. So we have this equation here, the third first order condition, and we plug in lambda t from the first order condition and lambda t plus 1 when we iterate this first order condition one period forward. And then we would basically end up with this expression here. And we see that again, the first term here only involves variables at time t, not at time t plus 1. So we can actually move this term here out of the expectations operator. We bring it to the other side. Here we have a negative sign, so that becomes positive on the right-hand side. And then we see that actually nt times 1 plus n is the same as nt plus 1. And this drops out altogether. And we have that on the other side, we have 1 over ct remaining here. And then we have beta. That beta here dropped out because we can divide it by beta to the power of t here. So we have 0 on the right hand side. So this beta here drops out, but this beta here still is present. And we have 1 over ct times 1 plus rt plus 1. And now this is the so-called Keynes-Ramsey rule that relates consumption at time t to optimal consumption growth, or expected consumption growth actually, depending on the relation between the discount factor and the expected interest rate in the future. And it's again basically the consumption Euler equation that we already know from the Ramsey-Cass-Koopmans model, that also relates, in the case of the Ramsey-Cass-Koopmans model, consumption growth, optimal consumption growth, to the difference basically between the discount factor and the interest rate. So if people are very impatient and the interest rate is low, then consumption growth is not as high because people consume more today and less in the future. And if by contrast people are more patient and the discount factor is high and probably also the interest rate is high, then the financial markets overcompensate people for their impatience and consumption growth would be steep. So they would consume less today and more in the future. The difference to the Keynes-Ramsey rule that we already know, or the Euler equation that we already know from the previous frameworks, is that we now cannot put ct plus 1 out of the expectations operator such that we would have a ratio of ct plus 1 divided by ct. That would be the consumption growth factor. But here we have to keep this term within the expectations operator because it's not yet known with the information that we have available at time t. But basically that's again the central equation. And we see that not much actually in terms of interpretation changed from the Ramsey-Cass-Koopmans model to the real business cycle model. We still have rather similar dynamics as far as the consumption savings choice is concerned. Now we solve the model for a very special case that is so simple that we can obtain analytical solutions. To this end, we assume that there is no government, so governmental taxes and transfers are set equal to 0, and there is full depreciation, so the capital stock fully depreciates between time t and time t plus 1, which avoids complications with respect to capital dynamics, so we don't have to carry over all the capital from the previous period all the time. That means the resource constraint is now that total output is equal to total consumption plus investment, where investment is the capital stock at time t plus 1, because the capital stock at time t fully depreciated until time t plus 1. And by the national accounts identity, we have that this is also equal to total income, the wage rate multiplied by total labor supply, plus the interest rate multiplied by the capital stock. And then, due to the fact that we have full depreciation, the interest rate becomes this expression here, where we have minus 1 instead of minus delta. And we can rewrite it also in terms of GDP or output, so that we have output here divided by the capital stock in the denominator. Now, we suppose that the saving rate as had is constant. So it's the same at time t and time t plus 1. Such that consumption at time t is 1 minus this saving rate, this constant saving rate, multiplied by output per capita, basically. And from this we can then determine the saving rate, but first we plug in consumption into the Keynes-Ramsey rule that we've derived on the previous slide. So here we have the Keynes-Ramsey rule, and we now plug in the expression that we have here for consumption on the left-hand side. And we also plug it in here on the right-hand side. And we plug in the expression for the interest rate from here. And of course, since the interest rate refers to time period t plus 1, we also have to iterate this one time period forward. So we would have yt plus 1 divided by kt plus 1. Now we have the saving rate as head in here, and we have the saving rate as head in here, and basically we can solve the Keynes-Ramsey rule for this saving rate as head, and that's what we do next. First, we note that the term that we have here, 1 over 1 minus s head, cancels out with 1 over 1 minus s head from here. And then we also note that we can rewrite kt plus 1 that we have here by s head times yt. So then we have this expression here and this expression on the left hand side. So that's the first step in simplifying. And then a lot of other things also drop out. So here we have that yt plus 1 and yt plus 1 in the numerator, they drop out. We can then write nt plus 1 here as nt times 1 plus the population growth rate. And we can cancel out this yt and this yt, because this yt here is again at time t, so the expectations operator, it can be put out of the expectations operator and can cancel off with this term. And this nt here and this nt here, they can also cancel each other off. So then in the end, it simplifies quite a lot. The only thing that remains on the left hand side is 1, because the denominator cancelled with this yt here, and the numerator with this nt, so 1 remains on the left hand side. And here we have alpha over s head, and we have 1 plus n in the denominator, and from the discount factor we have 1 plus rho in the denominator. And then we can bring s head to the left hand side, and then we have the equilibrium saving rate, basically s head star as alpha multiplied by 1 plus the population growth rate divided by 1 plus the rate of impatience, or impatience basically. And now we see again the saving rate decreases with impatience. That's intuitively clear. If people become more impatient, they save less today because they want to consume more today and less in the future. And if the population growth rate increases, the saving rate increases. So the converse holds true, and that we already also know from the Ramsey-Cass-Koopmans model, because there, if the population growth rate increases and we have a Benthamite utility function, then it's optimal to save more, to equip also the other members of the household that grows at a faster rate with the same amount of capital that the older members of the household already have, or the other members of the household. So the results with respect to the saving rate are intuitive on the one hand, and they are also this very much related to the results in the Ramsey-Cass-Koopmans model that we already know. So far, almost everything was rather similar to the Ramsey-Cass-Koopmans model, but now there is the new aspect that comes in, namely the endogenous labor supply decision. And for that we use the other first order condition that we had, or basically the two first order conditions, 1 and 2, that we merged into this static relationship between consumption, optimal consumption and optimal labor supply on the one hand, and the wage rate and the disutility of labor on the other. And in this expression we again substitute for consumption by the expression 1 minus s head yt divided by nt that we already had on the previous slide. We also substitute for wages by the expression that we have derived before, so it's 1 minus alpha times per capita output. And then in the result, for the number of people that are working in the economy, we can substitute individual labor supply, LT, multiplied by the population size. So if you all of that substitute into this expression here, we get this term here from putting in for CT. Then we get this term here for plugging in this expression for WT. And for this expression, we plug in LT, NT, and that's what we have here. Then again, we see YT divided by NT and YT divided by NT. Here they drop out. We can bring this B to the left-hand side, so that's then this B here. And we bring 1 minus LT in the denominator here to the right-hand side, and we have 1 minus LT here, and the 1 minus alpha, we bring it to the left-hand side so that we have it here. So on the right hand side, we then have 1 minus LT divided by LT, and this can be simplified to be 1 over LT minus 1 basically. And then what we want to have is we want to isolate LT because we want to get equilibrium optimal labor supply. So we bring everything to the other side. The plus, so the minus 1, we take plus 1, put it to the left hand side. Then we bring it to the same denominator, which means that we have basically 1 minus alpha divided by 1 minus alpha. So we have this 1 minus alpha here and this 1 minus alpha then in the denominator, because we flip it around, because we have 1 over LT here. So we flip numerator and denominator, which we also have to do on the other side. And then we would get this expression when we do all these reformulations. And here we see that this is a relationship between optimal labor supply and the optimal saving rate. But the saving rate we already know from the previous slide, so we can plug it into this expression here, and then we get endogenous labor supply only depending on parameters. And what we can show is that optimal labor supply depends negatively on B. So if the disutility of labor is higher, then people would ceteris paribus reduce their labor supply, and that's intuitively clear again. And if rho increases, then a similar effect holds true. Then they would also decrease labor supply, optimal labor supply, because leisure is also a normal good that people want to consume now. The important thing here is that this is a static relationship again, so it does not involve any dynamics, and that simplifies the whole thing quite a lot. So that's also the reason for why we can obtain analytical solutions here, because L stays constant over time, and so does the saving rate. And that implies basically that the decisions of households are static in this context, so they remain constant over time, but nevertheless there are dynamics, particularly in the level of output in the economy, and of course also in technology, because that's where the shocks come in. So what we can do is now we can write down an expression for the evolution actually of the logarithm of output. So if we take the logarithm of the production function, we would get alpha times the logarithm of capital KT plus 1 minus alpha times the logarithm of AT, of technologies, of productivity, plus the logarithm of LT, of labor supply. And then we can plug in some things here. For KT, we can actually plug in S hat, so the saving rate, multiplied by output in the previous period. So then we would get this expression here, alpha times the logarithm of S hat plus alpha times the logarithm of output in the previous period, yt minus 1. And here we could plug in for aggregate labor supply, L, the individual labor supply, times the population size, and then we would get 1 minus alpha times the logarithm of individual labor supply plus the logarithm of the population size. And here we plug in the evolution of technologies that we've written down at the beginning, which is 1 minus alpha from here, and then the logarithm of AT can be expressed as the logarithm of initial technology, the stock of initial technologies at time 0, plus the growth rate of technologies, GT, and then we have plus 1 minus alpha again from here, the technology shock A tilde. So that's basically the logarithm of GDP in this country. And now what we want to compute is actually not the level itself, but the deviation of the current level from the trend, because that's the fluctuations that we want to explain by means of this framework. So we denote by Y bar actually income or per capita GDP along the balanced growth path. So then we can write down the logarithm of GDP along the balanced growth path, where all these components would be present except for the last one, because the technology shock by definition pushes the economy away from the balanced growth path, so it cannot relate to the variable at the balanced growth path. But all the rest of the terms are here, just in their balanced growth path versions, basically. And then we can derive the log deviation. So the deviation of the actual logarithm of the logarithm of actual output from the logarithm of output along the balanced growth path, and we denote this by yt tilde, and that's then the deviation from the balanced growth path. And since we want to explain fluctuations, we want to explain exactly the deviations from the balanced growth path. We have already described the balanced growth path and its properties when we discussed the Ramsey-Cass-Koopmans model. The balanced growth path would be exactly the same in this framework here. But what we want to explain now are the deviations from this long-run balanced growth path, and that's actually exactly what the real business cycle model has been designed for. Now, what remains if we subtract the balanced growth path expression for output from actual output is y tilde alpha y tilde from t minus 1 plus 1 minus alpha times the shock of technology. And that is, again, this autoregressive process of order 1 with the innovation epsilon at. Now we can plug in this expression here and get one equation actually in output at time t minus 1 and technology at time t minus 1. And then from the first expression here, we see that we can express actually at tilde as the difference between yt tilde and yt tilde minus 1 and a function of 1 minus alpha. And then we can express this as such and plug this at again in here, but lagged by one time period. And then what we will get is an expression for output in the economy, or the deviation of output from trend output, so from the balanced growth path output, that is actually an autoregressive process of order 2. So here we can summarize the two terms that involve yt tilde minus 1 to one term, so that would be alpha plus rho a times yt tilde minus 1. Here we have rho a times alpha times yt tilde t minus 2. And here we have the innovation that comes from here. So this technology shock actually that hits at time t. And this means that we have an autoregressive process of order 2 that describes the dynamics of output in the economy. So that's a second order difference equation that fully describes the dynamics of output in this simplified version of the real business cycle model. So the fluctuations then follow an AR2 process where we have a positive correlation with the first leg. That's because alpha and rho a are positive, and a negative correlation with period 2 leg because rho a is positive, but here we have a negative sign. And now the adjustment patterns back to the long run balanced growth path depend crucially on the autocorrelation properties of the technological innovation, rho a. If rho a is moderate, so either positive or negative, but low in absolute value, then there will be a gradual phasing out. And the phasing out will be faster the closer rho a is to 0. That means if we have a technological shock or an innovation, then the economy tends to return to the long run balanced growth path rather quickly. If rho a is larger and positive, then what we can have is a hump shaped adjustment pattern. So then the larger rho a becomes, the longer it takes the economy to converge back to the long run balanced growth path. And it could be that the deviation from the long run balanced growth path in period 2 is actually even higher than the deviation in period 1. So that's this hump shaped adjustment pattern that we will see as an example later on. And finally, we could have a cyclical adjustment pattern if rho a is negative and rather large in absolute terms. So rho A is close to -1 basically. So that means we have a cyclical adjustment where in one period output is above trend, and in the next period output is below the trend, and we would have cyclical adjustment. So in the long run, the shocks would better out and the economy would converge back to the long run balanced growth path, but it goes once it's above the balanced growth path output and once below the balanced growth path output, and we have a cyclical adjustment patterns. And the good thing is that in this very simplified version of the model, we can calculate these impulse response functions, actually, as they are called. So the responses to a technological innovation of epsilon at, so a technology shock, actually even in a spreadsheet program such as Excel. So usually people would solve these types of models in a language like MATLAB or Julia and all these kind of numerical programs actually that are used to compute impulse response functions and so on and so forth. But for this very simple case, we can even do this in Excel, and that's what I illustrate on the next few slides in terms of a few examples. Now, the first example is a technology shock. So in this innovation epsilon at period 6 of size 1 over 1 minus alpha. Now this normalization just ensures that at impact the shock is normalized to 1 basically, because the shock itself is multiplied by 1 minus alpha here. Now here we do this for an auto-regressive coefficient of 0.5, and alpha is equal to 1/3. As said here, the shock hits in the 6th period, and as we are in the case of a moderate autoregressive coefficient, the effect of the shock will die out rather quickly on the level of GDP. Now here, this is implemented in Excel just by basically simulating this expression here with the innovation. And you get a deviation from the long run balanced growth path here up until period 6. There is no deviation because there is no shock, and the long run trend is the same as the short run series basically here. And then in period 6, which is here, the shock hits. The shock hits of size 1 basically. That's what we ensured by the normalization. And then afterwards it dies out over time. So here after about 10 periods after the shock, it's almost again undiscernible from the previous long run trend basically. So the shock dies out rather quickly with this autoregressive coefficient of 0.5. If you have a look at this on the level of GDP, the logarithm of it, then we would see that this shock is associated with deviation from the long run trend, but then the economy converges to the long run trend, and here it grows again with the constant growth rate of technological progress that in this example was just assumed to be 2% per year. So that's what happens with a moderate autoregressive coefficient. Now we can increase it to 0.8 actually, and all the rest stays the same basically. The shock hits again in the 6th period, alpha is 1/3, and yeah, nothing else changed. Now, however, we have a larger autoregressive coefficient, and that means that we will have a hump-shaped adjustment pattern. So again, until period 6, nothing happens, so the long-run trend is the same as the data that we have in the short run. Then the shock hits the economy, and then in the next period afterwards, there is even a further deviation from the long-run balanced growth path, and that's exactly the hump. And afterwards, the economy again converges back to the long-run balanced growth path, but this convergence takes much longer than in the previous example, where we see that here, even after 15 periods after the shock, the economy is still not yet back to the old balanced growth path. And from the level, the deviation looks like that. So it's hump-shaped, so the deviation goes even further away, so that the deviation is further from the long-run trend than before. And then we have convergence to the long-run balanced growth path again. Finally, we look at the cyclical adjustment pattern for an autoregressive coefficient of the shock of -0.85. Now, when the shock hits the economy, the deviation of output from the long-run balanced growth path is positive in the first period, and then negative in the second period after the shock, and then becomes positive again, negative again, and so on and so forth. So there is a cyclical adjustment pattern. The change or the deviations dampen off basically. So you have again convergence to the long-run balanced growth path, but it's in cyclical terms. And if we would have a look at the logarithm of output here, we would see again such a pattern that we have large deviations in the beginning, first positive, then negative, and so on, and then it converges back to the long-run balanced growth path. Now, this has really been a very simple real business cycle model, so the simplest model that one can come up with. But we've seen that even in this very simple framework, technology shocks can create cyclical patterns. Now, what's important in this context is that these cycles are not any deviations from underlying full employment economies or even welfare reducing deviations from this underlying full employment economy, but they are optimal responses of the individuals in the economy, mainly with respect to their labor supply decisions. Now, we have assumed only one shock at time t, but in principle, the economy could be hit by shocks at every time period, and these shocks could be positive or negative. And such shocks can then generate much more realistic patterns than the ones that we have seen here, so patterns that are more in line with the cycles that we can observe in the data. And in addition, and even more important actually, the model can be generalized in various directions such that these output trajectories are also more realistic. And that's what we will discuss on the next few slides.